Okay, this is the start of our unit on differential equations. About half of this is going to be stuff that you might remember from AB last year, and about half of this is going to be new stuff that we're going to extend for this course, okay? So today we're going to talk about slope fields. So what a slope field does is it lets you visualize a family of solutions to a differential equation. So a differential equation, recall, is something in the form of like y prime is equal to f of x, or in this case, they've written it as dy dx. Now, we could solve by taking the antiderivative of both sides, but remember, you get that plus c when you take a general antiderivative. That's why we're getting an entire family of functions, because we have all these different c values. Now, we've ended up with ones where you have plus c in all of these cases, but as we're going to see when we work with differential equations, it doesn't necessarily always end up working out that way, that it's just as simple as a plus c at the end. Okay, some differential equations can be solved algebraically, and the slope field for those differential equations can be used to verify that the algebraic solution matches the graphical solution. So if you know, for example, that it goes through y equals x plus 2, then you should be able to find that path on your slope field, okay? Some of them are going to be impossible to solve algebraically, which is why we like to generate the slope field, because it helps us get an idea of exactly what we're looking at, okay? Now remember that we can interpret dy dx as the slope of the tangent line to f of x. And so we're getting this geometric interpretation of what f of x is, the antiderivative, we're going to find the slope at each of the points and draw very tiny segments that represent the slope. So these are examples of slope fields, both of these here, okay? Now, here's what really helped me with this, okay? So these line segments show the direction that the graph of essentially the antiderivative is going to take, the original function. You almost see kind of the ghost of a family. To me, when I look at these slope fields, I see movement. I kind of see on example 1, it swooshes down from the top and turns around. You can kind of predict where it's going to start. If we just pick a single starting point, that would be considered our initial condition. And then here's the important part. You want to follow in a direction that is parallel to the line segments. It does not have to go exactly through one of your segments. That's always been something that's been kind of a challenge for me. I was taking it as more of a connect the dots kind of thing, trying to follow from one segment to the next. And that is not necessarily how this is going to work. So in this first example, the first one is the blank slope field. At the right, I've drawn some examples of possible solutions to that slope field, okay? Now, another way that they could ask, they could say, draw some solutions to this differential equation. And remember, what this equation is saying is the slope, dy dx, is equal to 2 times x. So in this case, the y variable doesn't matter. I got cut off there. Sorry if my voice jumped around for a second. So another way they could ask that is say, draw a direction field. That's the same thing as a slope field. Or draw integral curves. So that would be, if we took the antiderivative of, for example, 2, it's dy dx equals x squared, then we should get a cubic function. And you can see that marked in the slope field there. And so once again, we're not necessarily connecting the dots. We're just trying to kind of follow along. So maybe I wanted to choose this point to be my initial condition. Then I can see that my graph needs to kind of go like this. We want to be parallel to those segments everywhere that we are, and something like this. These are not going to be perfect. This is absolutely an estimate, okay? Now, to create a slope field, we just need to pick some values. And this is kind of tedious, so I went ahead and I'm using this where I've already filled this out. So in this case, notice that if dy dx is equal to x plus 1, the slope of the function is not dependent on the x value. So I just picked some different, or I'm sorry, it's not dependent on the y value. I just picked some different x's, and we had all of these dots here. So if I have x equal to -2, we plug it into x plus 1. So -2 plus 1 is -1, -1 plus 1 is 0, and so on. These, remember, are the slopes that we want to use. And since it doesn't depend on y, the slope for -2, -2 is going to be the same as -2, -1, the same as -2, 0. So at each of these ordered pairs, this is just the x. We're going to have a y coordinate, but when we look at these x and y coordinates, the only thing that is going to matter is the x. The value of y can be whatever we want. The slope, which is this column right here, will remain the same every time. So for all x values of -2, that would be this vertical line at -2 here. We drew a small segment with a slope of -1. -1, -1. And again, because the y value doesn't matter, it's going to be the same at all of those y values. A slope of 0 is easy to draw, a slope of +1. And really, it's hard to estimate what this whole column here is dy dx equal to 2, and this one is equal to 3. It's hard to imagine exactly what that slope is, but just make sure it gets a little bit steeper every time. We went from a slope of 1 to a slope of 2 to a slope of 3, so you see the line gets a little bit steeper every time. So these are really tedious to draw by hand. Your graphing calculator without a special app is not going to draw these for you. So this is really all you got. I've never seen one on the AP exam that asked you for more than 8 points. They usually don't ask you to do a whole graph because, as you can see, it's pretty tedious and time consuming. So example 4 is one where the y value matters, but the x value doesn't. The slope is all defined in terms of y. So again, if we pick in this table different y values and our slope, then the x doesn't matter. So at each of the different x values, you notice the slope stays the same all the way across because the x value doesn't matter there. So it's only going to be the y's where it is changing. So this is y equals 2, y equals 1, y equals 0, y equals -1, y equals -2. And so each of those is coming from multiplying 2 times y. So that's how we get -4, -2, 0, 2, and 4. So those are the slopes. And again, if you just compare, this is a very steep positive slope, a little less, negative, a little less steep negative, and then 0, and then we go to a steep positive and a more steep positive. And notice that even though my x is changing, my y staying the same, so all of those slopes remain the same. Okay, the last one, again, because this is a lot of points, let's just look at these 9 from -1 to +1 in either direction instead of graphing all of those points. Because you can see from the table over here, it gets kind of long. Now, I don't remember what this said before. I think y minus 1. That is a typo. This should say y minus x when you go to work this. So this is for dy dx equals y minus x. So for each of these ordered pairs, so we've got the ordered pair -1, -1, -1, 0, -1, 1, and then 0, -1, 0, 0, 0, 1, 1, -1, 1, 0, 1, 1. Those are all the ordered pairs that we've got here in our table. So this is dependent on both x and y. So for example, to get 0, this is -1 minus -1. To get this is 0 minus -1, and so on and so on and so on. And so let's see. I think I've actually got this incorrect on my notes now that I'm looking at this. This should be +1. This one is going to be 1 minus -1. So this should really be +2. This one is going to be negative 1 minus 0, 0 minus 0, 1 minus 0. This should be negative. This should be negative, and then that one should be 0. So there is an error on my PDF document there, so keep that in mind when you're working. But again, we just go then to each of those ordered points, ordered pairs. At the ordered pair negative 1, the slope is 0. So that's where we get this horizontal line. Negative 1, 0. The slope is positive 1, so it should really go this way. Let me fix that. Okay. Then we've got this one is also not going to be correct. This one should be positive 2. Then we get at 0, negative 1. This one should go the other way. Negative 1. 0 is correct. And then this one should also go the other way. And all of these other ones should flip around too. Sorry about that. So this one is 0. And then these two are going to go this way and this way. So that's kind of a mess. I'll have to fix that before I post the PDF. But that should be enough to get you started. So the homework assignment has some matching, drawing some slope fields. You're just kind of trying to get the hang of how these work. And that is it for your refresher on slope fields.